Well, today we're going to have a fairly short section. These are my notes, which I can provide for you also. They correspond to what's in the text. I just have some nice examples in here I'd like to present, so I'll do it out of my notes. And then you can try the homework. The one difference is that I'll make y a function of t where the notes makes y a function of x. Well, here's the kind of equation we're going to study today. It's only one kind of equation, dy dt plus p of ty equals f of t. A differential equation that can be written in that form is said to be a linear equation in standard form. This is sort of a summary of the concept here. Every equation of this form, it turns out, can always be solved, at least in terms of integrations. What the result is y, the solution function to this equation, where you're given p and f, is 1 over mu times the integral of mu times f, where mu is the integral e to the p of t dt. So if you give me p and f, I can immediately write down the solution of this differential equation. The trick is, first you have to recognize it's linear and put it into its standard form. This is actually a very important concept because a lot of models in the sciences are actually linear equations. And even the equations that aren't linear are usually too hard to solve. What happens a lot of times in industry is you'll say, well, I can't solve this, I'll linearize it. That means you write a linear equation whose solutions locally approximate those of the original nonlinear problem. So this is doubly important. This is one of the most used techniques. This, along with separation of variables that we did 2 times ago, are the 2 mainline techniques for solving first-order differential equations. Equations with highest derivative in there first. So here's the setup. Suppose I'm given this linear differential equation of first order in standard form, with p and f in here continuous. dy dt plus p of ty equals f of t. The way I can do this is simply to multiply through this equation by the integrating factor, they call it, mu of t equals e to the integral of p of t dt. So you put it in this form, whatever p of t is, you take e to the integral of p of t, multiply through the equation by that function, mu. Then it looks like this. Now, by the product rule from Calculus 1, actually, this is the derivative of mu times y. The easiest way to see that is to go backwards. You take the derivative of mu y, it's derivative of mu times y, that's this one. Derivative of mu, if e is e to the integral of p of t dt, its derivative, just by the chain rule, is e to the integral of p of t times p of t. So this is, this is the derivative of mu, is mu times p. So this is derivative of mu times y plus mu times derivative of y is the product rule here. So I just rewrite this equation using the product rule. And now I have derivative of mu times y equals mu times f, so I integrate both sides and I get mu times y on the left equals integral mu times f on the right, and I divide by mu and I get this result. There's that fundamental formula I told you. The solution is always y equals 1 over mu times the integral mu times f, where mu is e to the integral of p of t dt. So that's the proof. I think it's worth seeing it. It's insightful on how you actually solve these things. And actually it's of more importance when people solve higher order differential equations. They often write them as first order systems, and the same theorem applies to solving the higher order equations. So here's the theorem we just proved. A first order linear equation, I call 2.6 up here, with p and f continuous on an interval I, has solutions on I given by this formula. Right, so here's an example. Suppose I gave you this differential equation, t times dy dt plus 2 times y equals t squared. That's actually a linear equation. And suppose I want to solve this on the interval t greater than 0 or on t less than 0, one or the other. I can do it actually 2 ways, we've just discovered. I can either multiply through by the integrating factor mu and integrate both sides, or I can apply the formula that I got by multiplying by mu. In other words, up above, I can either go straight to the formula or I can go through these steps every time. Kind of like when you did quadratic equations. You can either complete the square and solve it every time. That was one way. Or you could just go straight to the quadratic formula, which is the formula you get by completing the square. So both ways work. Sometimes it's easier just to remember to multiply through by the integrating factor than to memorize the formula, but you can do either in either works. Suppose this equation is what I want to solve. Well, let's solve it first by multiplying by the integrating factor. In order to do this, I'll first divide through by t to put it into standard form. So I divide by t and it becomes this, dy dt plus 2 over ty equals t. Now it's in standard form, dy dt plus p of ty equals f of t. Right? I now can multiply through by the integrating factor e to the integral of p, 2 over t dt. Well, what's the integral of 2 over t? Pull the 2 out, integral 1 over t is ln of absolute value of t. So this is e to the 2 ln absolute value of t, plus a constant actually. You put a constant in here, but it turns out that you don't need it because this method works, if you look through the proof, with any antiderivative of p. You can pick any one you want. So let's choose c equals 0 just for simplicity. So we'll take e to the 2 ln of absolute value of t. Well, 2 ln t is ln of t squared by algebra, right? And e and ln undo each other by algebra. You just get absolute value of t squared. We can drop the absolute value because absolute value of t squared is the same as t squared, right? So now we'll multiply through this thing after we just divide by t, we'll multiply by t squared, because this actually makes the left side a derivative by the product rule, right? T squared dy dt plus 2ty is the derivative of t squared y. You just look at it and see that. It's always the derivative of mu times y, it turns out. We saw that above too. So if you just think about it, the derivative of t squared times derivative of y plus derivative of t squared times y, right? So we use the product rule to rewrite this as derivative of product. And now integrate both sides. We get t squared y on the left, and by integrating the derivative, they undo each other. Integral of t cubed is t to the 4th over 4. And now this time we do have to include this plus c. Otherwise, we won't get all the solutions. So for the integrating factor, you don't need to put the plus c. Any integrating factor will do. But to solve the differential equation, you need your plus c when you integrate it. You only get one solution instead of all of them. Now, we divide through by t squared, and we have the general solution of this differential equation. All solutions of it are t squared over 4 plus c over t squared, where c is an arbitrary constant that you have to determine by an initial condition. Remember last time we did all those solutions, we said you have this direction field, and here's the solution, here's the solution. When you pick the initial condition, then there's one solution that goes through it for a nice differential equation. And that picks off the unique one. But this is all of them right here. Now the alternative is to go straight to the formula, right? If we just use the formula, we just compute mu directly, e to the integral 2 over t dt equals t squared, same as before. But this time, instead of multiplying through by the integrating factor and integrating, we just say the formula is 1 over mu, integral mu f of t dt. So mu was t squared, so we take 1 over t squared, integral t squared times f of t, the function on the right in the differential equation was t. So we're integrating t cubed, which is t to the 4th over 4 plus c. Voila, right? There it is, in a quick result, right? Just like completing the square took longer in algebra, multiplying through by the integrating factor takes longer, but it's easier to remember the integrating factor than the whole formula. So here's the formula. The other trouble with the formula is the same as with the quadratic formula in algebra. When you apply the formula and you had c on the right-hand side, right? Remember let's write this quick warning out here about going straight to the formula. As in algebra, you had ax squared plus bx plus c equals 0. You could apply the quadratic formula to that by putting a, b, and c in. But if you had ax squared plus bx equals c, if you had this form, it was easy to accidentally put this in for c and get the wrong result out of the quadratic formula, because, right, when you subtract it over, now it's minus what it was on this side, you get the wrong answer. Same thing can happen here. If you apply this formula before you put the equation into standard form, you'll get the wrong result. So there's the other danger of the formula. If you use the integrating factor method by multiplying through, then you'll see it's not working out right. But if you just go straight to the formula, you better make sure it's in standard form first. All right. So here's, let's see. Here's another example. This time I'll give you an IVP, initial value problem. These words in differential equations are all so long that we tend to abbreviate them. All right, so here's the differential equation. 1 over t dy dt minus 3 over ty equals 1, together with the initial condition that when t equals minus 1, y equals 1. So we write y minus 1 equals 1. This one will come up with a unique solution, right? It's the differential equation with an initial condition. So before we can apply our method, we have to have this linear equation in standard form. We multiply through by t, and it becomes dy dt minus 3y equals t. Right? Multiply through by t to get this. And now, obviously, it's a linear equation in standard form. Dy dt plus p of ty equals f of t, where p is minus 3 and f is t. So we go to the integrating factor formula. E to the integral of p of t is e to the integral of minus 3 is e to the minus 3t. Again, we can leave out the constant if we want. And so this time we'll just cut straight to the formula and say, oh, it's 1 over mu integral mu f of t dt, where f of t is t and mu is e to the minus 3t. And let's see, it's 1 over e to the minus 3t is e to the plus 3t, and an integral of e to the minus 3 times t. You can do that with an integration by parts, right? You put u equal t and dv equal to e to the minus 3t dt. And with this method, for a small power of t times e to the kt, you can always do that. So you use integration by parts and you come up with this result. And then an arbitrary constant, don't forget that, or you won't get all the solutions. And now you've got c e to the 3t plus e to the 3t times this, the e to the 3t and e to the minus 3t cancel, and you get minus t over 3. And again, the e to the 3t and the e to the minus 3t cancel here, and you get minus a 9. So here are all solutions to the differential equation. But now I want to apply that when t equals minus 1, y equals 1. So I put that into here. I put in minus 1 for t, and I got plus 1/3 minus 1/9 here, equals 1 over here, and I solve for c. Here's the equation I get when I put in that initial condition. And c, if you add these over and divide by and multiply by e to the 3, you find out that c equals 7 e to the 3 over 9. And so now you put that back into the formula we had up here, put this in for c in the solution, here it is, put that in for c, and you got y must be 7/9 e to the 3t plus 3 minus t over 3 minus a 9. There's the unique solution to that initial value problem. All right, this actually has an important consequence in numerical analysis. There are lots of these equations where you get this nice result, right? This always gives you the solution. But alas, you can't do the integral. It's too hard. So what do? Computers are very good at estimating these integrals numerically if you're given the initial condition. And so if you use this particular integrating factor where you go from t0 to t, and this thing here, this will be outside the test. I won't put this on the test, but I'll just point out to you that computers can do this, can estimate these integrals very accurately when you have an initial condition together with your differential equation. So that nice result, the formula, is actually quite useful for solving these on the computer by approximation. All right. Well, that's the point of this one here. Let's try one more here. Suppose I want to find the unique solution of dy dt equals 2t times y plus 1 together with the initial condition y of 0 equals 1. Well, once again, it's not in standard form. I first have to subtract this part of this over, the part that has y in it, but leave the 2t times 1 over here to recognize that it actually is a linear equation in standard form. So you put it into this form. Now you can use that formula where if you go from t0 to t, you get a particular integrating factor, this one, e to the minus t squared. And then when you plug it into the formula, 1 over mu integral mu f of t dt, if you go from t0 to t on this thing, this gives you the unique solution straight off, and you don't have to worry about the plus c. And the computer can estimate this very accurately even when you can't do this by hand. All right, so sometimes it's worth writing it just in the form of an integral. I'll leave that there then. Try the homework problems, and please send me emails if you have questions. I can send you back some equations on email, actually, in this form. So let me know how it works out.